All right, here's the second day of 2.2. We're still working on synthetic division, higher ordered polynomials, remainder theorem, this type of stuff. Okay. First question here. I just want to review how to set up synthetic division. We're going to practice it plenty. So I'm not going to work this one all the way through. All right, I have x plus 4, which is in the correct form to use synthetic division. So my value for k would be negative 4. That would be my divisor. And then I'm just going to use my coefficients. I'd use 4, 0, negative 6, 0, 10, and negative 3. Okay, and to get that started, I bring down 4. Negative 4 times 4 is negative 16. Again, add those two. Which would be negative 16, and so on and so forth. Okay, and again, whatever you get for the remainder, that means p of negative 4. If I plugged it in and evaluated it, I will get whatever remainder I get there. All right, again, I'm not working that one all the way through, largely due to the fact that you will get lots of practice with synthetic division. Okay, now if we worked backwards, okay, we haven't done this yet, but I just want to show you that it wouldn't be the end of the world if we had a polynomial and we had the divisor and then we're given the quotient with the remainder of negative 1. It would not be the end of the world if we had to solve this. Okay, to set this up, it would mean that p of x divided by 3x minus 4 equals our quotient of x to the third plus 2x plus 2 minus a remainder of 1 over 3x minus 4. Okay? That's what we'd have. If I wanted to get p of x by itself and find the original polynomial that I divided by 3x minus 4, I would just have to multiply both sides of the equation by 3x minus 4. Okay? Now, what's going to end up happening there is that's going to cancel out the bottom part of the remainder when those are multiplied. So what you're going to have left, okay, is the quotient times the divisor minus the remainder. Okay? So p of x is going to be the product of the divisor and the quotient minus the remainder. To get the standard form of what that polynomial is, we just have a bunch of foiling, a bunch of distributing, and simplifying to do. Okay, the key here is to get it set up like this, and that you know to multiply both sides by the divisor. All right, let's get some roots. Let's find some roots. Okay. What's going on here is you'll see with higher ordered polynomials, we typically have a goal when we're finding zeros, is to reduce what we have down to a quadratic. Okay? The reason is when it comes to finding zeros, quadratics are easier to deal with. Okay? So we try to divide out factors and reduce what we have down to a quadratic. Okay, that's what we try to do. And you'll see so far today, for us to get started, we have to be given one of the roots. Okay? And find the rest. So if we had a quadratic, remember that's going to have 2 roots. If we had a 6th degree, and we won't see many 6th degree polynomials, but it would have 6 roots total. So it's good to know how many we're looking for so that we know when we're done. Here's a pretty typical problem that we're going to see in this lesson. We have a 3rd degree polynomial, and we are told that one of the zeros is x equals 1. Okay, well, that's fantastic. It's actually very important that we're given one. I'm gonna go find the other two. Okay? Now, very important right here. If there's a 0 of x equals 1, that means this cubic has a factor of x minus 1. Okay? Now I'm going to divide out this factor, which is in the correct form. Remember, to do that, it's got to be x minus k, to use synthetic division, that is. And this one is. So I'm going to take all my coefficients here, and I am going to divide by x equals 1, and I'm going to do a couple things. I'm going to verify that 1's a 0. I'm going to verify that x minus 1 is a factor. Okay, and to do all this, I need to get a remainder of 0 when I do my synthetic division. So I bring down the 1. 1 times 1 is 1. Negative 12 plus 1 is negative 11 times 1, still just negative 11. Adding those together, we get positive 24 times 1 is again just positive 24. Add those together, we get 0, which is good because we verified that 1 is indeed a 0. But here's what we also did. That's the much bigger deal. P of x, which I'm calling our original third degree polynomial, could be broken down into two factors. I just verified that x minus 1 is a factor, and now I'm very interested in what I had left over. That would be 1x squared minus 11x plus 24. Now, thinking back to that slide that we just looked at, we verified this factor, which we were kind of given because we were given the 0. This part right here, we were told there was a 0 at x equals 1, which I still verified, so I did some work with that. But now, I've got this down to a quadratic, and I want to find the two remaining zeros. Again, remember that zeros is synonymous with roots. I can just find the two that are left from this quadratic. And the nice part there is quadratics give us options. I can check to see if it's factorable. I could try to complete the square, which typically no one ever likes to do because it's the hardest of the three. And also you could use the quadratic formula. But largely due to the quadratic formula, if we can take out a factor of a polynomial that's higher than degree 2 and get it reduced down to a quadratic, we always know we can find the remaining roots. Okay. First thing I'm going to check here, is this thing factorable? Are there two factors of 24 that add up to negative 11? And you bet there is. You bet there is. You bet there are. I don't know which one's proper English. Either way, we've got two of them. All right. Now, I'm finding the roots here. And again, this factor of x equals 1 led to a root of x equals 1. This right here means there is a root of x equals 3. That's one of the two that was missing. And there's one at x equals 8. Okay. So again, I used this 0 to divide out this factor and find these two remaining roots, 8 and 3. That was so much fun, we need to do it again. Okay? We need to just do it again. Same thing here, all right? Same darn thing. If there's a 0 of negative 5, that's implying that there's a factor of x plus 5. Let's do some synthetic division. To 1, verify that 5 is indeed a 0, and to get this cubic reduced down to a quadratic. Bring down the 1. Negative 5 times 1 is negative 5, plus 0 is negative 5. Negative 5 times negative 5 is 25. That adds up to negative 6. Negative 5 times negative 6 give us 30. Add those up and we get 0. Which means negative 5 is a 0. X plus 5 is a factor. But again, here's the bigger deal. When I take out that factor of x plus 5, that means x squared minus 5x minus 6 is what's left over. The reason that is sweet is because it's a quadratic. Quadratics are easier to find the zeros. Okay? There's a lot of different ways that we can do it. Just like the others, I'm going to check and see first, because it's by far the quickest way to find the zeros, is to see if this is factorable. And I believe it is. I'm looking for 2 factors of negative 6 that add up to negative 5. X minus 6 and x plus 1 will do the trick. Those two numbers, negative 6 and 1, those have a product of negative 6, and they add up to negative 5. Again, x plus 5 means there's a 0 at x equals negative 5. That was the one I was given. I did synthetic division to find these 2 remaining zeros of negative 1 and 6. All right. Let's take a look at one. Notice what we have here. We have a 4th degree, all right, with 2 zeros, one that would imply that x minus 1 is a factor, and the other would imply that x plus 4 is a factor. And notice the original polynomial that I'm given is degree 4. So to pull this off, I had to be given 2 of the 4 zeros. When I have a cubic, at least where we're at right now, when I have a cubic, I can be given 1 0 and I can find the other 2. With a 4th degree, I need 2 to find the other 2. Okay? So the only thing that's going to be different here is I'm going to start by verifying that 4 is a 0. I've got 1, 2, negative 9, negative 2, and 8. All right, I'm going to go through, do some synthetic division here. This would be 4, 6. 4 times 6 would be 24. Negative 9 plus 24 would be what, 15? 4 times 15 would be 60. Something here has gone terribly wrong in terms of verifying that this is a 0. Okay, let's go back into my first thought here is, did I miss any gaps? We have 4th degree, 3rd degree, 2nd, 1st, and 0. Nope, it's all set up good. 1, 2, negative 9, negative 2, and 8. That looks good. Let's keep going here and see what happens. 4 times 15 would be 60. Negative 2 plus 60 would be 58. This would give us a large remainder and would not verify that negative... Oh, easy, sorry. Silly mistake here. Back it up, back it up. All right, I'm running out of time. All right, so here's the deal. That should be... And again, this has happened before, and it's always good to show you it can happen to anybody. It's usually negative signs. Verify that that's a 0. I should have been using negative 4. Verify that that's a 0. Then do it again with 1. Verify that 1's a 0. Then you'll have it down to a quadratic. All right? We'll call it quits there.